then we can of course solve, and when we solve we find these things, that this V cap and P cap are given by these formulas, all right. So, now you see that before we go into this, so here these are the points basically where the Rayleigh lines and the Hugoniot curves are intersect, and these are the P cap and V cap solutions plus minus 1 will, as we will see what this will come into what this actually represents. So, first thing is that the first thing is that you see this part, for this equation to be true, this part should be less than 1, because it has a to the power of half. For it to be real, this part has to be less than 1. If this part is less than 1, this is 1 minus this part, this whole thing has to be less than 1. Okay. So, because it is 1 minus something, right. So, when it is 1 plus minus 1, this part is essentially always, even if it is minus, you have this sign, then this part is always positive, because this part is always less than 1. So, then it means that the sign of this guy, that is V cap minus 1, is essentially only given by this part. Okay, that is 1 minus mu square. Okay. This is very important, because now you see that then you can write to determine the sign, or to do the full thing, that is V cap plus minus 1 is equal to 1 plus essentially 1 minus mu square times gamma plus 1 times mu square, all right. So, you see now we have that, and also for this part similarly for P cap, you see this now P cap is given by, that is only the sign part is given by 1 minus mu square divided by gamma plus 1 times gamma, because also by the same argument this part has to be less than 1, right. This only this part, because otherwise 1 minus this thing should be negative, then it can be imaginary just because of this square root. Okay. So, this whole part is always less than 1. So, when this whole part is less than 1, then this 1 minus this part should also be less than 1, but then it means that it is always positive. Okay. So, the sign of this thing, that is P cap plus minus 1 is equal to, then sign is only determined by this part, that is 1 minus, if you take this 1 to this thing, 1 minus mu square divided by gamma plus 1 by gamma, gamma plus 1 times gamma, right. Now let us consider the situation when mu is greater than 1. So, when mu is greater than 1, what you see here is that this is 1 minus mu square, then this thing is inherently negative. Okay. So, when this thing is of course, you have these things, that is you have also this parts, but when you have you see when you have mu essentially is greater than 1, then this thing is essentially negative, and you have essentially P cap essentially is greater than 1. Okay. And also you have and similarly for the other situation you have let us arrive at this just 1 second. Yes. So, what we were discussing is that we will consider this part of the equation. Okay. So, when we consider this part of the this equation, that is equation 6, we will just go back a little bit, that is when we have since we have an exponent here which is to the power of half. Okay. So, this is essentially a square root. So, for the inside of the square root to be real, for the square root, the solution of the square root to be real, the inside of the square root must be greater than 0, right. So, then it means that this 1 minus this whatever you have, this part should be less than 1. Okay. Now, for this part to be less than 1, if this is less than 1, then this is 1 minus this, then this whole thing is less than 1, right. After you get the square root, this whole thing is less than 1, right. Now, this is 1 minus 1 plus minus this. When it is plus, then 1 plus, say let us say this is then 0.5 or 0.6. So, then 1 plus 1.5 is of course its positive number, but when you have the negative sign, this is 1 minus say 0.6, then also it is positive. So, under all circumstances, you see this quantity is positive. We do not have to determine what mu is to know that this quantity is positive. Similarly, for this V cap also. Now, then what I want to say is that then the sign of this guy, is only determined by 1 plus 1 minus this, or only is purely determined by this part, okay, right. Now, say what happens when your mu is, we will consider two cases, mu to be greater than 1 and mu to be less than 1, okay. So, when mu is greater than 1, then this is 1 minus mu square, mu is greater than 1, so means 1.2. So, mu squared is 1.44. So, 1 minus 1.44 is invariably negative. So, then this part is minus and this is also minus. So, minus 0.44 or something. So, then becomes plus. So, then in that case pu plus minus 1 cap becomes is equal to 1 plus some more positive quantity. So, then it means that p cap plus p plus minus 1 cap is inherently greater than 1, okay. And because if you go back to the Rayleigh lines, that when p cap is greater than 1, v cap has to be less than 1. So, then it automatically means that v plus minus 1, because this is obtained by the intersection between the Rayleigh and the Hugoniot lines, is less than 1, okay. So, similarly, let us consider case 2. We will come back to what this case calls. So, similarly, we come back to case 2. So, now mu is less than 1, okay. So, when mu is less than 1, this is 1 minus mu square, this part then it becomes 1 minus mu square is inherently then positive, okay. So, then this minus and a positive quantity, then it retains the minus sign, then it becomes p cap plus minus 1 is essentially 1 minus a positive quantity which is less than 1, of course. So, it becomes less than 1. So, when mu is less than 1, p cap plus minus is less than 1 and also v cap plus minus becomes greater than 1, okay. So, and as a consequence of this here, your rho cap plus minus if you have is greater than 1, is less than 1 for mu less than 1, and for rho cap plus minus is greater than 1. So, for case 1, if you have mu greater than 1, okay, your p cap. So far in the Rayleigh lines of this, the Rayleigh lines did not tell us that, it just told us that when p cap is greater than 1, v cap is less than 1, or when p cap is greater than 1, rho cap is also greater than 1, okay, or vice versa. When p cap is less than 1, your rho cap is also less than 1, but did not tell us in what regime this happened. So, by considering the intersection of the Rayleigh and the Hugoniot lines, we just find out that when mu is greater than 1, that is oncoming, if your wave is stationary and your flow is coming, the reactant or the reactant flow is coming at a speed which is supersonic, mu greater than 1, then the pressure, okay, if the chemical wave is consuming the reactants at a supersonic speed, then the pressure rise will be greater than 1 and the density rise will also be greater than 1, and that we will call to be a detonation state, okay. So, here basically the wave, because it is restrained by continuous feeding of the reactions, if we make the wave free, that is if it can propagate by having a fixed, having a quiescent mixture which is not flowing, if we have a mixture which is just present and just static which is not flowing, then the speed at which will propagate, if it is supersonic, then the pressure will rise downstream of the wave, okay. And now similarly, that is called a detonation state. So, and then consequently or similarly from this it arrives also that this that if the wave speed is subsonic, that is if the speed of the reactants at which it is being fed to the chemical wave, if it is subsonic, or if the chemical wave is propagating at a subsonic speed, then essentially your p cap will be less than 1 and your v cap will be greater than 1, but your density ratio should be less than 1. Okay. So, this is then the very important concept of the difference between deflagration and detonation. This is one of the most important central concepts in combustion of what is the difference between deflagration and detonation, and that arrives by considering of this intersection of the Rayleigh and the Hugoniot lines. As you see, then the difference is nothing but the fact that when mu is greater than 1, P cap is greater than 1, V cap is less than 1, rho cap is greater than 1, and that is called detonation. And for deflagration, your mu is less than 1, your P cap is greater than 1, your V cap is greater than 1, and your rho cap is less than 1. So, in a detonation, pressure rises, density rises. In a deflagration, pressure drops, density drops, and that comes from consideration of pure mass, momentum, and energy relations. Okay. And of course, this P cap and rho cap are nothing but the density ratios and the pressure ratios, that is a PB by PU, rho B by rho U. Okay. So, this is then that is why then this branch is essentially a supersonic branch going back to this thing, and this branch is essentially a subsonic branch, mu greater than less than 1. Okay. So, this is the so then this is the point that we were making. Now, there are some more interesting features that comes associated with it, that yes, we will just summarize them. What are the properties of the detonation and the deflagration waves along with the interesting properties. So, in a detonation wave, as you see, the pressure and the density increase across the waves. Okay. And we will get two solutions, because you see that it came like P cap plus minus. So, plus minus corresponds to this things, that when you consider this to be plus, okay, when you consider this plus sign, your V cap, you consider the V cap plus, or when you consider this plus sign, you consider the P cap plus. When you consider the minus sign, you consider V cap minus, and when you consider this minus sign, you consider the P cap minus. So, that is why there are two solutions. And then there is also an interesting point, that is a tangency point, that is, this is the point, tangency point. So, you can have a state that instead of the Rayleigh lines directly crossing through or intersecting through the Hugoniot lines, you can have a state where the Rayleigh lines essentially is a tangent to the Hugoniot lines. Okay. So, what does a tangent mean? Tangent means that the slope is same, slope of these two lines are same. And also another thing is that the strong and weak detonation that we are talking is that the upper point. So, if you have a Hugoniot line like this, this is your Hugoniot line, okay, for a given QC, and this is your Rayleigh line for a given mu. So, this upper intersection point is called the strong detonation point. Strong, why? Because your pressure rises even higher. So, you see this pressure rises higher, and this is another point, that is why the plus minus sign comes, and this point is essentially the essentially the weak detonation point. So, this is the strong detonation point, and this is the weak detonation point, and this is the tangency point, which is the Chapman-Juge point, okay, the upper Chapman-Juge point. So, and it will be seen that there is nothing called a weak detonation that does not exist, because you will see that essentially what happens is that it can be shown by by setting QC to be 0. There is actually then you will see that this point does not exist, and definitive exists, that is an unphysical solution, because you will see that entropy essentially is by entropy considerations, you will see that this does not permit this weak detonation point to be satisfied. Okay. And this is also comes from the wave structure, basically, that that there is no weak detonation, and also the CJ detonation wave is prevalent, whereas for the deflagration wave, sorry, there is no entropy consideration for this. This is just comes from the wave structure, that there is no weak detonation. So, this point does not exist because of the waves, wave structure of this thing, whereas as we will see later that this point is also not very common, whereas the detonation typically propagates at this speed, which is the upper CJ point of the Chapman-Juge point, which is essentially the tangency between the Rayleigh lines and the Hugoniot curves. Okay. Now, we will find that out, and then going to the deflagration waves, that is the mu to be less than 1, we will find that the pressure and the density actually decrease across this wave, right. So, that is the most important difference between deflagration and detonation. I mean, this is the central point that one must always, a combustion engineer must always know, that what is the difference between deflagration and detonation waves, apart from the many things, that the fact that the deflagration waves propagate at subsonic speed, when unrestrained, or here we are considering in a wave stationary frame, that is, so everything is coming in. So the rate, the speed of the incoming mixture is essentially supersonic or subsonic. But if we were if we could place our observer on the burned gas or the on unburned gases, we will see the flame of the chemical wave to be approaching us, and in that case we will see that it is approaching us at either supersonic or subsonic speed. If it is approaching at a subsonic speed, then it is a deflagration. If it is approaching at a supersonic speed, then it is a detonation. And then the other properties are, the most important properties are that the pressure and the density decrease across the deflagration wave, whereas the pressure and the density increase across the detonation wave. Okay, and this also gives you the two solutions, the strong and the weak solution. And the strong solution is the strong solution, which is the large pressure drop, that is this point P cap is much less than 1, that is ruled out, and that comes from the entropy consideration, because I will see that the entropy decreases by crossing such a wave, so which does not is the second law of thermodynamics does not allow, and whereas this is the weak deflagration, and this is the thing. Also interesting to note is that this is, you see that this point is very close to, this P cap is very close to 1. So this we can go back again to our previous consideration, that when the Mach number is small, if you remember that we arrived at this thing, right. So that is we arrived at the fact that for order 1 change in u du dx, you need order Mach number square change in pressure, these were normalized, right. Pressure, if you remember from the previous classes in the governing equation. So we see that when the Mach number is small, which is the case here, from thermodynamics or from the governing equations, we again arrive at the fact that your pressure drop is small, whereas in the case where pressure drop could have been large in the strong deflagration state, that does not exist. So that is why you see in this region your pressure drop is small. Okay, and that is your weak deflagration case, that is the common flame, a premix flame that you see in the gas burners, in the aero engine, in the power generation engine, in a gas turbine engine, in a ramjet engine, in a SI engine, typically, except when there is not knock. So that you see this essentially this deflagration. Deflagration is diffusion control, whereas detonation is essentially a shock controlled phenomena. It's obtained by shock heating. Okay, so whereas in the deflagration you see that the pressure rise can be huge. Okay, you see this is large, very P cap is much greater than 1, whereas here is P cap is slightly less than 1. Okay, so there is a small pressure drop, but not huge. So this is the point. So this gives a very important ideas about the combustion structure and about what happens and the characteristics of the deflagration and the detonation waves. Okay, and as you have said that the deflagration wave is prevalent and this is isobaric. It is very difficult to stabilize a detonation wave. What do you see that the advantage is that in a crossing a detonation wave you have a large pressure rise. So can that be utilized someday? Can we have combustion pressure rise? Whereas in a gas turbine engine, one of the parameters engine designer looks at is a pressure drop. That is obvious, because if you have a premix combustion happening inside a gas turbine engine or even non-premix as such, you will have actually in a gas turbine engine it's a mix of premix, non-premix and partial premix combustion. But say for the sake of argument you have a premix flame inside an aero engine combustor, so invariably what you have is you have a pressure drop. So in the thermodynamic diagram, if you in the TS diagram, if you do, this pressure drop will actually result in loss of efficiency, right. Whereas in the detonation you see that gives a rise to a huge pressure. So it is of interest to understand how basically the detonation can be stabilized, but because detonations are very fast, as you will see that it propagates about few kilometers per second, right, almost. So we need to understand and this mechanisms well. And we also, another important unresolved problem in combustion science is essentially how can we even transition a deflagration to a detonation. Well, that is an open problem. That is still a very much of a research issue, this deflagration to detonation transition. Okay. So now then the Chapman-Jouguet detonation points you will see, and that is the tangency point. So we have basically two Chapman-Jouguet detonation points. Just erasing these things. So these are the two Chapman-Jouguet detonation points, these and this. Okay, so this is the upper CJ point and the lower CJ point. The upper CJ point, which happens when mu is greater than 1, that is of very high interest for the detonation, because typically the detonation propagates in this CJ point, and there you can, at this point, a very interesting thing emerges, that you can essentially from those relations you can find out this tangency problem, because it means that your dp dv cap obtained from the Rayleigh lines is equal to dp cap obtained from the from the Hugoniot lines. Okay. So, this from the combined solutions you can obtain the mu Cj actually. That is a very beautiful thing that comes out, and so instead of even specifying the wave structure, you can find out this this Chapman-Juge velocity, and this is the velocity with which a detonation actually or a Chapman-Juge deflagration propagates, and of course the MB is equal to 1, that is a bond gas Mach number should be equal to 1, and this is once again that strong and detonation your MB is actually less than 1 greater than 1, and strong and weak deflagration your MB that is a mass bond MB is actually greater than 1 and less than 1. So, from here also you can understand that for a strong deflagration your MB becomes greater than 1, which is not physically possible, and so the only the thing that is possible is essentially a weak detonation, and similarly you will see that your only also strong detonation for your MB is less than 1, which is physically possible. So, with that we will close this class, and then we will go into the deflagration waves, the details of the deflagration waves. In this class, in this course we will not go into detonation, because it is a very specialized topic, as still a lot needs to be known. So, here when we say flames or when we do combustion, we will essentially implicitly mean that we will do deflagration, and that is we will cover in the next course. Thank you. Next class. Thank you.